we are going to prove that the product of -1 and a is equal to -a for all a element of the set of real numbers. Now, this might seem too obvious, but of course, we are still on the review on the algebraic properties of real numbers needed and essential for the topics of preparation for real analysis. So we are going to show the proof of this with regards to the use of the properties of real numbers and not automatically assume that they are actually true, to which we already know in our usual setting. So we are starting with this proof here, and our goal is to start from this left hand side and to arrive to our right hand side using again the properties of real numbers. But first, we are going to let a be an element of real numbers so that we are restricted to the real numbers setting. So from this, we are going to have, then, let's introduce our left hand side. You have -1 times a. And from this, we need to use the properties of real numbers in order for us to show that this expression is just equal to the right hand side expression, which is -a. So I'm going to use here, okay, the most common property of algebraic property of real numbers used in proving similar situations like this is the additive inverse, or by introducing 0, which can be expressed as the sum of inverses. So since we are just adding zeros, so we are not changing the value of the product of -1 and a. Okay, so with that, let us now rewrite our 0 as a sum of inverses. Specifically here, of course, this is -1 times a. Let me use here a plus -a. Take note, they are both inverses, so if they are added, they are just equal to 0. Hence, we are not introducing any other expressions, but they are expressions equivalent to 0. And this is the point sharing to this one, because we are reintroducing some algebraic properties, specifically here, the additive inverses. Why are we doing this? The goal of that is later, we can use the associative property of addition, because by looking into this step, we have now introduced -a, which is the end goal of this proof. Okay? We are not automatically assuming this is equal to -a, but with the use of this method, we are reintroducing -a. So again, we are going to use here associative property of addition, where we regroup them using the first. So we have here, let me use bracket in this case. You have -1 times a plus a, the positive, then you will have here plus -a on this side. Okay, we have used here again associative property of addition. Okay, so from this, we need to look into this expression, because we would like that to be reduced, as we already have -a intended for our right hand side. What we could do here in the previous video was looking into the idea of inverses, but here we cannot automatically use inverses here, because this is not -a, it's still just a. We have not simplified -1 and a yet. So we are not going to use here the inverse, additive inverse, but we are going to use here the distributive property, since we have, or factoring in this case. So we have the reverse of distributive property, as we have common terms. So we can factor a, leaving on the first term just -1, and since once we factor a here, we leave it with 1 in this case, plus -a. By doing that, what is left on our grouping symbol are just exact values of -1 and 1, and we can just simply simplify them into 0. Okay, plus -a. Okay, we have the -1 and +1 equal to 0, and the product of this, now we can do that because it's 0 times a. So you will have here 0 plus -a, which then gives us -a. Again, this property is very obvious. The product of negative 1 and a is negative a. But since we are relearning some things and the process of proof needed for real analysis, so we are doing this method, reintroducing algebraic properties of real numbers. And with this, thus, we have established that this left-hand side, negative 1 times a, is just equal to this right-hand side of negative a. And once we have proven this in the future setting, we can automatically use this property as we have shown that here. That's the purpose of this video, just as this disclaimer. Again, this is very obvious, but we are doing this so that we could establish some rules and necessary properties that we could use later on as part of our understanding on topics involving real analysis. But this time, this is the proof for the said statement. Thank you very much for watching.